Interested in the FoxAlien 4040 XE machine? Then stick around because that's what we're going through today. Hey everyone, and welcome to another episode of James Dean Designs. In today's episode we're going to be taking a look at the FoxAlien 4040 XE CNC router machine. Now, if you're not familiar with FoxAlien, they're a manufacturer of desktop CNC routers and laser machines, primarily in two different sizes, a 3018 and a 4040, which is what we're going to be focusing on today. Now this is the base model with the spindle. You can buy some upgrades for this, such as a laser module or even a larger spindle mount to take something like a DeWalt router. Now what we're going to be covering in this episode is we're going to talk a bit about the specifications and go through basically what you actually get for your money. We're then going to move on to building the machine itself and finally doing a test cut and then a bit of a review at the end, just to sum everything up. Now if you're just interested in certain parts of the video, as always there will be timestamp links in the description below. Definitely do check out the description area, that's where I'll put all the useful information, any reference to different parts that we use today, and also links to things like the Patreon page so you can continue to support the channel. But for now, let's move on and talk about the specifications of this machine. Now this machine has an operating area of 400mm by 400mm, which is pretty big for a desktop CNC machine. It has a Z travel height of 65mm, which once you take out a little bit of safe height travel room means you can easily machine 55mm deep, maybe even 60mm. Now the other measurement you're going to want to know is the footprint. How big of an area does this actually take up? Now excluding the control box, because that can be moved around, it is 670mm by 760mm by 360mm high. Now any eagle-eyed people will notice that first measurement I gave is different to the one on the FoxAlien website. There's a valid reason for this. Once you move the x-axis all the way forward, this drag chain actually sticks over by an extra few centimetres. Now it is a critical measurement because you need to know that to ensure that the machine can operate at its full parameters. It's also really important if you're building an enclosure, for example, because you don't want the drag chain hitting the enclosure. So FoxAlien, if you are watching, please update that measurement because it is very important. Now the spindle on this machine is a 300 watt 24 volt air cooled spindle with a diameter of 52mm. It is pretty powerful. It can obviously cut through softwoods, hardwoods, acrylics, plastics, other soft materials. I think it can do soft metals as well, maybe some things with hard metals also. Now I'm not 100% sure of this, but I'm fairly certain it is correct. This control unit can take the upgraded spindle, the 500 watt version of the same model. But if you are planning on going down that route, please just do check with FoxAlien first to make sure the power consumption can actually be taken with it. But as I say, I am fairly certain it can. Now the machine itself is driven by NEMAT 23 motors, which for a machine this size is ideal. There are 4 of them driving this machine, one on either side of the y-axis, one on the x-axis and one on the z-axis. Now with the exception of the z-axis, they are driving belts. This is a belt driven machine. They do have some useful advantages. One, they are a bit quieter, so if you're running this in a house or an urban environment where you need to keep noise as minimal, then it is something to consider. More importantly, they have better acceleration values. So if you are doing something like laser work where you need the higher acceleration values to stop the overburn and things like that, then obviously belt driven machines is definitely the one for you. Now on each axis there are limit switches, which are great safety features, stop the axis running too far. Also means you can run a homing sequence, which is brilliant for referencing coordinates and being able to return to a certain position without having to worry. I think that is all the specifications for the main machine. Let's move over to the controller itself. Now first thing you notice straight away, obviously it has a screen. It has an offline controller inbuilt into it, which is a brilliant feature. I mean, you don't necessarily have to have a PC or laptop around. You can just load your jobs onto a memory card, insert that in the front and run the job without the need of additional machinery. Now the other thing you'll notice on the front is the dial. The dial is for the speed of the spindle. This is a manual speed control spindle. Now what that means is you still need the M3 command within your software to turn the spindle on, but you can control the speed via this dial. Should you find it's going too fast or too slow, you can just adjust it during the job. You'll also notice it has an emergency stop on the top. Again, a brilliant safety feature. Should you need to stop a job midway, you can just hit that down and obviously it will shut the machine down completely. There are a few switches on the side of the machine. One is to go back and forth between the control unit, the offline controller and the PC. It just needs to know where the input of information is coming from. The other one is to switch between laser and spindle. Again, it just needs to know what it's operating so it knows how to control the power output for that. So I think that's all the specifications for the machine itself. So with the specifications out the way, let's move on and get it built. But before we do that, I just want to mention Loctite thread locker, specifically the blue one. Now if you're not familiar with this, I've spoke about it in previous videos, but it's like a soft glue for all the nuts and bolts, and it just helps hold everything in place and together. Now as well as applying a bit to the new bolts you're about to put in, you may want to also consider taking out existing bolts one by one and just applying a drop to those and putting it all back together to ensure everything stays safe and in place. Specifically some of the small tinier grub screws that are in the pulleys and things like that are known to come loose over time, definitely apply a bit to those. Now you won't actually see me use it in the video purely because if I have to reshoot anything, to take it all back apart with this in place can be a bit difficult and can get a bit messy, but it is definitely something I recommend you use. So let's move on and start to get the machine assembled. Now it may sound obvious, but the first thing you'll want to do is unpack everything in the box and check it against the packaging list that's also inside that box to make sure everything is there. Also take the time to inspect all the components and check they're in the condition that you expect, including all the connections on the wiring. You also want to take the time to make sure that all of your axes move freely. Now there's no real scientific method, but one way that I like to do it is stand it up on its side like this, and it should be able to hold its own weight. You should be able to move it up and down without applying too much pressure, and as I say, when it's left it should stay in position. Now if yours are too loose or too tight, you may need to slacken these off here and apply a little bit more pressure with these bolts and then tighten those up to get the correct holding. Just to show you an example of one being too loose, this is the X motor, and if I release it you'll just see it slide down slowly. So that just means there's not quite enough tension on it. So what we're going to do is release these, apply a bit more pressure with these two bolts here and tighten these back up. A good indication is these are actually loose already, so that's probably why this slides down on its own. So I've just adjusted this setup slightly using the Allen keys provided, and as we can see it now holds its own weight. With a little bit of pressure it does move, but most importantly it stays when it's left. So before we actually start assembling, we're just going to do a check to make sure how square the frame is and how perpendicular the sides are to the surface it's sitting on. Now when we start talking about how square the frame is, what you might find is that something is skewed one way or the other, or that it's tapered one way or the other. And the reason this is important, let's say for example we have a skew. As the y-axis is moving backwards and forth, you won't have a straight line, you'll actually have a slight diagonal line. So it's not going to give us great results. And if we have a taper, for example, the axis will jam as it moves back and forth. So all this is just to ensure that the machine runs as smooth as it possibly can. And when we're talking about perpendicular, we're talking about how vertical the sides are in relation to the surface that it is sitting on. Now instantly when we talk about something being square, people probably think of just getting something like a speed square and going into the corner. The problem is there's a slight gap between the two pieces of extrusion, so it's very difficult to use a speed square because you can't get the both surfaces to meet. Now we can try and get around this by using something to pad out one side or to block a corner. So for example, your spindle holder should be fairly solid and square, so you could put that into the corner and use your square on there to get an idea of how accurate it actually is. But the issue with that is on the opposite corners we still have the stop bracket, so it's not perfect. So we need to look at other methods to see how square it is. The easiest method is just to measure the diagonals and see whether the measurements are the same. You can either use a tape measure or get a piece of wood and do it off that. Obviously not this piece of wood, it's a bit short, but you see the principle that I'm aiming for. You can mark up on the piece of wood, mark up with a pencil on the piece of wood and do it the opposite way. We're going to do it with the tape measure today. So we'll go from one corner to the other and make a note of that measurement. Be careful that you are measuring the same spots on both corners because obviously it will dictate the measurements. And do the opposite corner. Now, ideally, both of those measurements should be exactly the same. If you find that they are different, it means something is not square. If your machine isn't square, we need to work out exactly what's going on with the frame. The way we're going to do that is we'll take a measurement of the width at the front and we'll take a measurement at the width of the back. We'll also then take a measurement of the depth on the right hand side and the depth on the left hand side. Now, if both of your measurements on the depth and the width are equal with each other, what that means is something will be skewed. So it means that something may be like that or the opposite direction. If you find that one set of measurements is the same, but the other set of measurements is different, then it probably means you've got a taper. And what I mean by that is, let's say the measurements on the depth were exactly the same, but the measurements on the width were different. Let's say the front is wider than the back. What that means is you have a tapered frame like that. The reason this is important to know is because it determines what corners you work on to solve the problem. If you have a skew, you work on opposite corners to get it back into square. So for example, you would slacken two corners off, readjust the frame a little bit, tighten them back up, and then take the tension back off by releasing the screws and tightening them back up on the two opposite corners after you've done that. If you have a taper, you will work on two sets of corners on the same side. So in our example that we just said, where the back is tighter than the front, you might slacken off the two sets of screws, the two sets of bolts at the front, try and bring it in a little bit, and then release the ones at the back and take them out a bit to try and counteract it. So let's take a quick look at one of the corners just to see what we can do to try and help resolve these issues. So each corner has 4 bolts holding the frame together. You'll have 2 bolts per piece of extrusion. The bolt on the top is just holding in the belt in place for the tension. Now, if you're trying to get rid of a skew, which is where you're working on diagonal corners, you'll release all 4 bolts, take the pressure off them by turning them anti-clockwise, readjust the corner a little bit and then tighten them back up. If you're getting rid of a taper, you will release whichever 2 is relevant to the piece of extrusion that you're working on. So in our example, we will release the bottom 2 and move the side out or in as much as we possibly can to counteract how square it actually is. Now, when you take one of these bolts out, obviously there's a hole drilled through the plate and it's about 0.5 millimeter worth of play. It is not much, but in most cases it will be enough to get your frame fairly square. If you need more play in it, you may need to drill the hole out just to give you that extra little bit of play. And while we're focusing on the corner, we'll look at how perpendicular the sides are. So I'm going to bring my combination square in and just put it up against the edge. Now, as we can see, that is fairly accurate. If you find that you have a gap one way or the other and that it is slightly tilted, what you need to do is release 2 bolts on the front and the back and twist it left or right to take out that tilt that you have, and then obviously tighten the bolts back up. So if you do have to adjust any of the corners, then make sure you keep checking those diagonal measurements until you get them exactly the same. The closer you can be with your measurements, obviously the more square your frame is going to be. So with everything square and with the sides perpendicular, we're now going to move on to the next stage, which is mounting the bed. Now within your frame is a series of pre-drilled holes or pre-threaded holes. There should be 5 on the front and 5 on the back. The middle 3 are for the wasteboard or the bed, whatever you want to call it, and the side ones are for the dust baffles. Now there is a front and a back to the wasteboard, so do pay attention. The front has more holes than the back does. So we position this in place and I'm just going to put that over the holes now. And what we want to bring across is our pack of bolts, and we're going to take out the M520 bolts, and there should be 6 of them. Now what we're going to do is drop all 6 bolts in place. We want to tighten them up but not too much. You still want to have a little bit of play, and then we'll finish off by pinching them all up at the end. So we'll quickly drop them in, align them with the holes and start tightening them up. I'll speed up the camera now because you don't need to watch all of this in full detail. So with them all in place, we're just going to pinch them up now. So we're just going to put that extra 1/2 to 1/4 of a turn to make sure they're all tight and in place. What I would also suggest doing after this stage is to just go back with the tape measure or whatever method you do, just to make sure everything has stayed square. It should do in theory, but it is just a safety precaution. So let's bring in the dust baffles now. We're just going to drop one of these on either side. should just slide it in there. We'll do that. And again, you have the pre-drilled holes or the pre-threaded holes that these will sit on. Push your baffles up to the board as much as you can. And for this, we're going to need the M5 16mm bolts. We're going to do the same again, just drop them in, take them close to being tight but not quite pinched up all the way, and then we'll come back at the end and just finish them off. Again, I will speed this up so you don't need to watch it. So next we're going to fit the X-axis gantry. To do this we obviously need the gantry itself. We also need the M5 12mm bolts with the spring washers and the flat washers. If you're in any doubt, the spring washers go on first, followed by the flat washer second. The other thing we need to do is make sure that our carriages are the same depth from the front on either side, just to make sure that everything lines up correctly. Now you can either do this with a tape measure and measure them both and do it manually like that. Or what I find is a simpler method is to take something like a piece of wood, drop that in place, bump one carriage up to it, take it over to the other side and do exactly the same there. And we now know those are both the same depths from the front. So we're going to roughly place this in position, get it as close as we can so we can see that drops in nicely. What you can do to begin with is just rest it on the brackets at the back while you get the bolts ready. And then we'll try and slide this into place and get one of the bolts in. Obviously once you've got one in, you can work around and do the other three. As before, we'll just leave them loose so there is a little bit of play to get the others in position. And once in, just pinch all of the bolts back up. The next step is to attach the Z-axis assembly to the X gantry. Now your carriage should be about halfway down, and what you should see is that there are 4 holes in the back that are drilled through the extrusion, and these are where the bolts will go to mount it to the gantry itself. For mounting we will need 4 of the M5 25mm flat cap screws. So we'll load one screw up to begin with and just place that in and then try and get this in position. Now these are self-centering, but it is worth noting that there is a tiny bit of play on them. And what we need to do is make sure this is squared up shortly. So we're going to get the one in place and then put another one in. And obviously work through all 4. As usual, just leaving a little bit of play left at the end so we can readjust anything if we need to before tightening everything up. Now the reason we want to leave a little bit of play in there is because we just want to bring our square back and see how square this setup is. Now that is actually pretty good. There's no gap on that at all, so I'm really happy. But obviously if it is slightly out, you may need to twist your Z-axis setup one way or another and tighten it up to counteract it being out. I will just check it from the front way as well to be sure. That's pretty good. Let's tighten this up. And what we'll do after we've tightened it up is just recheck it again to make sure it hasn't moved too much, because obviously the more you tighten it, with them being self-centered, it can just pull it out a little bit. So we'll pinch this last one up now and put the square back against it. So as a quick tip, you can't get in with the Allen key in on the short end to apply as much pressure as needed. So use the long end, but use one of the clamp brackets that come with it to apply a bit of extra pressure. So simply place that in there, place it over the Allen key like that, and you can use that just to add a bit of extra torque and pressure to tighten them up. At this point I would also recommend going around all the different bolts and making sure everything is tight. With the only exception is the ones on the backlash nut. These should have pressure applied to them, but they shouldn't be too tight. You'll know if you've gone too far because you won't be able to move your carriage up and down like that. Such as if I pinch this one up just a little bit, I mean that was what, quarter of a turn, it locks the carriage. So that's basically the difference. You want it to have tension on it, but not too much that it stops it from moving. Next we'll be installing the spindle mount. Now the cool thing about this is there are 4 grooves in it ready to take a laser, so it's actually dual purpose for a spindle and a laser. Now on the Z-axis assembly there are 3 threaded holes on either side. I don't think it matters whether you use the top 2 or the bottom 2, but in line with the instructions we're going to put it on the bottom half of the Z-axis assembly. Now when you put the bolts through the holes, which by the way are the M5 55mm bolts, you'll notice there is a little bit of play in them. So once you start to tighten this up, do check it is square just to make sure everything is as accurate as it can be. So we'll put this in place now, and as before we'll just get it in with a few turns, get another one in place, and then we'll go around, put all 4 in and pinch them up at the end. Now I'm nearly ready to tighten this up, so I'm just going to bring my square back in, rest it on the bed and see how accurate this is. Just needs a very slight twist and we'll pinch it up there. Now remember, you only want to pinch up the ones on the left hand side because we haven't put the spindle in place yet. So we'll tighten these up and then we'll move on to installing the spindle. So let's slide in the spindle. It should go in quite easy if you haven't tightened these up. If you have tightened them too much, obviously just release them out a little bit so this can drop in. Now what you want to do is have around about 10mm hanging out the bottom of the spindle. So I'm just going to hold it there for now and pinch these bolts up on the right hand side just to hold it in place. And we'll do this one. It hasn't got to be exact, but you just kind of want a bit hanging out the bottom as well. You don't want it tucked up too much in the mount. Now with that in place, I'm just going to pinch everything up with a bit more torque. So let's get the 2 brackets attached for the Y drag chain. Out of the 3 brackets, it's the 2 larger ones, so we'll get rid of the smaller one for now. We'll also need 4 of the M5 6mm bolts. So let's get this in place. This first bracket shouldn't actually sit on the surface, it should be mounted off it by maybe, I don't know, 5 to 10mm. You do have a little bit of play within the bracket itself with these slotted holes. So we'll just pinch that up slightly, get the second one in place, and then tighten them both up together, leaving that gap underneath. And there, that one's done. Now this second bracket sits underneath the motor just back here. So again, let's get that in place and do exactly the same. And there we have both those done. So let's move on to the X1 now. So we'll move on to fitting the X-axis drag chain bracket and the lower support. So we'll put this in place now, using the 4 remaining M5 6mm bolts. This just sits to the side of the motor. Now for the larger support, this has 2 brackets on either side which we're going to mount it to, and it should sit with the clips underneath. So we'll get these in and start to get it in place. So now we're going to get the drag chains and cabling in place. There's no real easy method to do this, but what I suggest is start at the one end with the X bracket here, lay the chain across the support, fix that in, and then do the same on the Y bracket and leave your cabling at the side. We're going to be using the last set of bolts, which is the 4 M4 6mm flathead screws. So let's move the drag chain over and start to get this laid out. The open side of the drag chain should sit on top of this and then fold back over to meet this bracket here. Whenever you're working around fixing these in, be quite careful because you don't want to catch none of the wires in this area. This can be a little bit delicate moving all the cables out of the way, and the threads are also very fine, so be careful when placing them in, but you should be able to do it quite easily. And move them to the other side, put the other one in. And as always, just make sure it's pinched up at the end so that we know it's not going to come loose. We'll do the same at this end now. that's all in place and secured. Now when you come to lay the Y side of the chain, you want to make sure that there's no unnatural twist within the cabling. So just be careful when you lay this out. We'll pull this wire out of the way for now. This will get fixed underneath the chain support shortly, but we'll focus on fixing this in place first. So I had a bit of a twist in the cable which I just wanted to take out and make sure this sat as best as it could. Now this does feel very stiff going over the Y motor, but that is where it is meant to be based. So we'll just get the remaining screws and start to get this in place. Let's just secure the Y motor cable now. Those should just pop into the little clips and then clip into place. We'll do this for all four underneath here. Make sure the cable is secure, and now we can move on to getting all the wires connected. So when it comes to wiring everything up, it's fairly simple. Everything's colour coded, marked up with what goes to what. The different types of connections are also different. So for example, the motor connection is different to the limit switch sensors. So we'll just work around now and get everything connected up. X motor to X motor, get that in there. Z motor to Z motor, get that in there. And I'll just work around and do the rest of the connections. Now we're just going to make the last connections. Now I'm unsure why, but FoxAlien should have put some sort of support here to take the weight of the cable to stop it rubbing and catching on anything. So definitely do consider putting some sort of support or zip tying it there. Now connecting up the spindle's really easy, positive to positive, negative to negative. What I would say is these are actually a little bit loose for the pins that they're connecting to, they're just pulling off too easy. So you may want to just put it in place and crimp it with a pair of pliers just to ensure that it stays in. Squeeze it, that's held on a bit better now, and then we'll do the same for the other side. And just connect the sensor up. So for peace of mind, I have just quickly zip tied this on. I may come back later and print some sort of 3D bracket to go here, just to make sure it's supported a bit better, but at least holding it in place just ensures these connections should stay much safer. So let's move on and get everything connected. As we've already mentioned, everything is clearly labelled up so you know what goes where. Even the Y1 and the Y2 are marked up separately. So let's get it all connected. So with everything connected, I should also mention this is obviously where you connect your USB cable, your laser if needed, and also the Z probe. We're also going to quickly connect the Z probe, and I'll show you how to set this up shortly. So we've connected the power cable and we're going to turn this on for the first time. Make sure your E-stop is being released. Sometimes it's depressed like that. You just need to rotate it and let it release. We'll press the on and off button. And as you can hear, everything fires up. We've got the FoxAlien logo. And what we're going to do to begin with is just click control and do a couple of tests, make sure everything is moving correctly. Whenever you start your machine up, it will go into an error state. To release this, you need to press unlock. So once you've pressed that, we're going to go to move. Now as you can see, you've got the directions, the Y, the X and the Z as well, and also to turn the spindle on and control the speeds or return to the previous menu. We're going to press step. And as you can see, that's just gone to 0.05, 0.1, 1mm and 10mm. So we're going to move the head around a bit and just make sure all the directions work. We'll go left a little bit, send it back right, bring it towards us and send it back. And we'll also do the same with the Z axis. We'll bring it up and take it back down. And we're just going to fire the spindle up as well to make sure that works by pressing the spindle button. As you can hear, that's kicked in. We use the knob here to control the power. As we bring it down, so does the speed of the spindle. It will eventually stop if we take it too low. And we'll just bring it back up again, up to full speed and stop it. Excellent, we know everything is working as it should. Let's move over to the computer and run a test cut. So with the machine built, we can move forward and get a test cut done. But I thought this was the right time to talk about maintenance and checks we should be carrying out regularly anyway. Obviously, when you're assembling your machine, make sure that you are checking all the pre-installed bolts to ensure they have been tightened sufficiently. These machines travel miles around the world when they're being transported, and things can come loose. So just ensure that you go through and check every single bolt on this machine. Particularly some of the little grub screws that are in the pulley wheels, they are quite small and they need to be tightened up correctly. It's also the perfect example of where to use the Loctite that I mentioned at the start of the video. Now there is also maintenance we need to carry out, such as the thread rod on the Z axis. These need to be lubricated, and we're talking about dry PTFE based lubricant here. You want to avoid anything such as grease. That is a bad lubricant to use because it will hold on to the dust and at some point it will clog up and probably cause a failure. We also want to keep an eye on the belts themselves. Now over time these may start to lose tension and it can cause things to come out of a line, miss steps, and generally cause you problems. If you do need to tighten them, this is how you do it. If you find that over time your belts start to become loose, it's easy enough to put the tension back in. First start by releasing the bolt that's holding it into the extrusion. Then slowly release the bolt that's holding it into the plate. This will take more tension out of the belt and allow it to go a bit slack. At this point you'll want to use something like a pair of pliers or grips to grab the remaining bit of belt that is sticking out from underneath this clamp plate. Hold it tight at this point. Release the clamp plate and pull the belt as tight as you can get it with your hands, and then tighten the clamp plate back up via the two Allen bolts. Obviously this should be a bit more taut at this point. You can then come back to the bolt that's on the back plate, tighten that back up, and it will pull all the tension back into the belt. Finally, tighten the bolt up that's holding it into the aluminium extrusion, and that will just secure everything in place. And lastly, you just want to keep an eye on your electronics and wiring. Obviously as parts move around, you want to ensure all your connections stay secure and make sure that no wires are rubbing anywhere. It can cause electrical problems, again leading to a failure, so do keep an eye on all of those as well. Let's move forward and get a first test cut done. So we need to fix our material down to the bed, and we're going to be using the MDF board supplied with the kit. We also need to install our bit into the spindle. Now a top tip here, always fit your material down before installing the bit. The reason for this, if you're moving your hands about and you've got a sharp bit installed, it's very easy to catch your hands and injure yourself. Now in regards to holding the board down, we could use the clamps supplied with the kit. These do a great job of holding it down. They apply sufficient pressure, and obviously you've got all the threaded inserts in the board. However, I do find them a bit cumbersome because with the height that they stick up, I often worry they may catch on the bottom of the spindle. Now if you've seen any of my previous videos, you'll know my favourite method is CA glue and blue painter's tape. Today we're going to be using Starbond. It's a brilliant product and holds everything down really well. One of the benefits to this method is there is no clamps around your material, so you can use every inch of the board. I'll quickly show you how we do this now. So you apply a layer of tape both to the bed and to the bottom of the material. We're then going to put some CA glue on one side and the activator on the other side and stick them together. It takes literally a few seconds for the glue to set, so you have to be quick. And once it's in place, you just hold it down literally for a few seconds and everything is set. Now that doesn't move at all. So we'll move on to installing the bit now. Now we're going to be using one of the 20° V-bits that come with the kit. I always try and leave the cover on before you actually need to start cutting, just for safety, because those are extremely sharp. Now some bits have a slightly chamfered edge, some bits have a flat edge. These have a chamfered edge, so they can just slide in quite easily. But what you may need to do with more difficult bits that have a square edge is actually take the collet nut completely off and then insert it into the hole and re-thread it back on. Now you want to make sure that the bit is tucked in there quite well, and ideally at least 1/3 of the bit should be tucked up into the insert. So we'll just make sure that is in there, and we'll use the spanners provided with the kit to tighten everything up. So now we're over at the PC. What we're going to do is install the driver which allows the PC to talk to the machine. We're then going to open up the software for running the machine and do a test cut. So the first thing you'll want to do is plug in the memory stick that came with the machine. And when it opens, you'll either see a zip file like this or a folder named the same thing. If it is a zip file, you'll need to extract it first. I'm just going to extract it straight to the memory stick itself. This will take a second. So with that done, we'll head into the folder and we're going to be loading it in for Windows. And we want to go to Software and then Driver. Now before we click this, some machines require the device to be connected, so at this stage I would advise plugging your USB cable into the machine. So we're just going to open up the driver exe file, we'll click yes and then click install and let it run through installing the driver. And there we have the message to say it's been successful. Click OK and we'll close this down. Now at this point you'll want to double check that everything has installed correctly. The easiest method to do this, come down to Start and type Device Manager and open this up. Once in Device Manager, come over to Ports, click the drop down and you should see something similar to the driver that we just installed, CH340, and that's on COM11. We need to remember that number because we'll need it shortly. So we'll close that down. We're going to go back up a level into the software folder. And we want to open GRBL control, or Candle as it's more commonly known as. This is the software that you use to run the machine itself. Now what I would suggest is putting this somewhere usefully on your desktop on your C drive so you can run it regularly rather than having to do it off the USB stick itself. Now I've already got this installed on my desktop, so I'm just going to minimize this down and open it from my desktop. And we just want to click the Candle exe file. Now once you're in Candle, you want to come up to Service, go down to Settings, and where it says Connection and Port, you'll remember that we just had COM11, so we'll click the drop down menu and select COM11. You also want to check the baud rate. Now by default this usually does load as 115200. If it is showing a different number you will need to change it to mirror what we have here. Now the other thing that we can set up while we're at this screen is the Z probe. This is quite simple to do. You should have a line of code already in the probe commands area. If not, I'll copy and paste this into the description below the video so you can use it yourself. Now there are two important numbers to note in this line of code. The one is after the Z minus where it says 20. Now this is telling the Z probe how far you want it to travel down in order to try and find the base. I like to keep mine at a relatively low number, something like 20 or 30 millimeters. You can make it more, but this just avoids too many issues if for any reason you run the command and the base for the probe is not there. The other important number is the second number after this Z here. Currently it's saying 20.86 because that's off another machine that I use with the Z probe. But this is where you'll want to insert the measurement for your new Z probe. You'll need to know the depth of the Z probe base itself. Using a set of calipers is the easiest method. And there we have 14.83. Now as we've already taken the measurement as, we know it is 14.83. So we'll enter that in. Now this is a brief run through of setting up the Z probe. If you're after a more detailed explanation, check out the link in the corner to a previous video where I set the Z probe up on a different machine. I cover a lot more detail. I also go through how to check the measurement of your Z probe if you don't have a set of calipers. Now I also have a custom button set up to return to 0. Now I cover this in more detail again in the previous video, but if you want to do the same yourself, I'll also paste this code in the description. You'll need to put it in button 1 and you'll also need to scroll down a little bit further and have user commands turned on or ticked here. So with all those settings done, we'll click OK. Now what we can just see is this has switched to an alarm mode and we've got a bit of extra code appearing in the console over here. This is a positive thing because we know it is now connected to the machine. Your computer will connect to the machine purely off the power supplied through the USB cable, but what we'll do at this point is now turn the power onto the machine. You may hear the fans kicking in the background. So as I previously mentioned when we were using the offline controller, whenever you start your machine up it will go into an alarm state. This is just a safety feature, and similar to how we do it on the offline controller, we just simply click the unlock button and that allows us to start using the machine. I will briefly run through the layout of Candle. This top half is the visualizer. This is where it will display all the G code that we're about to be cutting in a visual format. The bottom half is where it will display the code that it is sending back and forth to the machine. and on the right hand side we have the tools panel, or the different things we can use to control the machine. We'll scroll down slightly to see the jog control. Now again, like the offline controller, this is how we can move the machine about. You have steps here, which is the amount of millimeters it will move each time. You can either select a predefined option, or you can simply type over with a measurement yourself. The feed rate is the speed at which it will travel. So if we clicked one of these buttons now, it would travel 20 millimeters at a feed rate of 1000 millimeters per minute. Obviously, the higher the number, the faster it will travel. The lower the number, the slower it will travel. And what I should also point out is the step rate is the same whether you're moving the X, Y or the Z axis. So now we've put these measurements in, let's just move the head about and make sure that everything runs as it should do. What we're going to do now is load in one of the test files off the USB stick. So we'll come up to File and we'll go Open, and we'll head over to the memory stick, go into the folder, Windows and Test Code. Now I'm just going to use the FoxAlien one to begin with, so we'll click that and click Open. And as I just mentioned, in the visualizer you can see the visual representation of what it's going to cut, and then down here you can see the code which it will send in order to achieve that. Now what you notice over here is all these arrows. This is the start or the 0 position for the job. So we need to align this with the bottom left hand corner of the material and tell the machine that is where we want it to start. But what I should point out is if you're using code that you haven't created yourself, you need to check that it is within the same measurements as the material that you're using. And if we come down here, we'll see a couple of measurements. This is the X, the Y and the Z. So we know it's 118 millimeters wide by 41 millimeters on the y-axis, and then it will travel a maximum of 4.3 millimeters in the height. I can rotate this round, and what we can see there is these red lines represent the height that it will be traveling, which is to say is the Z-axis. The piece of material that we've fixed down to the bed is 200 millimeters by 100 millimeters, so we know that it's more than sufficient. Another thing when loading in test code is you may not know how deep it is expected to cut. Now we can see from this visualization it is only going to be doing one pass, which means it will do one cut across the entire surface of the material, but we don't know the depth of it. Now there are some clues when you come down to the code, and what we have down here is Z minus 0.5. This will mean after we've set the 0, we know it's going to travel down 0.5 millimeters to make the cut, or half a millimeter basically. So once we've engraved this, it should be half a millimeter deep. So let's move on to setting the 0. We're going to jog the head over to the bottom left hand corner of our material. I'll speed this up quickly. Now we're roughly in place. I'm going to take the cap off the end of the bit. What we're going to do first is set the X and Y 0, and then we're going to do the Z probe, which will determine the height as well. I'm going to bring this step measurement down to 1, just so we can control it in finer increments, and then we're going to move it about a little bit and try and get the tip of that bit right on the corner of the material. We'll lower the Z axis down, and just move it back a little bit, and then left. Maybe a bit too far. There we are. That's pretty much on the corner of the material. So at this point I'm going to click this button here, which is the 0, X and Y. Now what we're going to do is run the Z probe command, but what I always like to do is run the Z probe command from slightly inside the material, just so that the base can sit level on the piece of material. So we're going to type in 20 steps. We're going to raise the Z axis up by 20 millimeters and then move it in diagonally. Oh, one click too much, bring that back. And then place the Z probe underneath. Clip the alligator clip to the bit. And then run the Z probe command, which is this magnifying glass with the down arrow. We'll remove the Z probe out of the way. Now what that's basically just done is the machine has measured where the Z probe is. It then knows to add on that measurement that we took earlier, the 14.83 millimeters. And now what we can do is that custom button that I mentioned earlier, we'll come back up to the user commands and we're going to click 1, which is the custom button, and as you can see from the pop out, it will return to 0, 0, 0. And that's just a good test to know that you are starting in the correct position on your material. Now we are pretty much ready to go, but one thing I would suggest is before you start any job, because this machine has a manual speed control, just make sure your speed is where you want it to be. I always turn the dial all the way around to the right to 100% and then just turn it back a little bit so to around 90% power. But obviously different materials will require different strengths of power. So with that done, let's click send and get the job started. So as that went so well, let's have a bit more fun. We've got a piece of MDF sprayed black here. We're going to stick that down again with the blue tape and the star bond. If anyone is interested, there's a link in the description for this with an exclusive 10% off code. It is brilliant stuff and I do recommend it. I'm also going to change out the bit for a 0.5 tapered end mill. I just find these a little bit more versatile than the V-bits that come with the machine and well worth the investment. So as we've put a new piece of material on the bed, we'll need to reset the 0 again. So I'm quickly just going to jog this about, raise the Z axis up a little bit and bring it back towards the bottom left hand corner of the material. Lower the Z axis down to try and get it a bit closer. That's pretty good. So again, we will reset the 0 for the XY. We'll click that. And then we'll do what we did before. We're just going to raise the Z axis back up a little bit. And move it in about 20mm diagonally. So 20mm right, 20mm forward. And then we'll run the Z probe. Take that out of the way. And then we'll load in our new test code. I've created a little design which I've saved on my desktop. There we are, and as we can see it's just my logo and the FoxAlien logo. Now what I will point out here, you may see this orange line. The 3 arrows down here are where the job starts, or your 0 position. This orange line indicates where you set the Z probe from. So it is just useful if you need to come back and set the Z probe in the same position. It gives you an indication of where you originally did it. So I'm just going to come over and make sure my 0 is correct. So I'm going to go back up to my user commands and click that custom button we created. Perfect. So all there is to do now is let's set the job off. So after doing those 2 test cuts, I continued to play with the machine off camera, and I have to say everything went really well. There was a small issue where it missed a few steps, and the only reason for that, there's a bit too much tension on the Y wheels, so I released it by a quarter of a turn. Everything continued to run smooth. Small error, easily corrected. Now, what I do really like about this is the size of the cutting area versus the footprint. It's a great ratio. You don't lose too much space with all the extra machinery around the outside, and it still easily fits on a desktop or work surface. So, you know, it is a brilliant ratio between the two of them. I also love the fact you get the offline controller inbuilt. Now, I don't use offline controllers typically because I'm always next to a PC. However, it's a nice feature to know that's there, and it means I can technically take the CNC anywhere and not have to worry about how I'm going to run it. Now, it wouldn't be a rounded review if I didn't talk about some of the areas that could possibly be improved. One thing I'd like to see improved is a bit of a thicker X-axis gantry, just to make sure there is no extra wobble in the Z assembly when machining, especially if you are trying to machine harder materials. I think it would also benefit from an extra support somewhere underneath the bed. With it being MDF, I'm a bit concerned it may sag over time. However, that may not happen given how thick the piece of MDF is, so I guess only time will tell. FoxAlien, if you are watching though, do consider those for future upgrades. In saying that, I am still happy I have this machine in my workshop. You get a lot of machine for your money, and it is extremely versatile, especially if you consider something like the laser upgrade as well to make it dual purpose. So definitely a great machine for the money. If you are considering buying it, then please check out the affiliate links below. It doesn't cost you any extra, bro, just get a tiny little bit back to help keep the channel running. And in saying that, thank you to all my patrons for continuing to support me. It really does help. That is the end of everything for today's episode. I really hope you enjoyed it and found it useful. As always, please give it a thumbs up and subscribe if you enjoyed everything. And if you want to chat to me, comment below. I always try to get back to everyone. But that is everything for today's episode. I'll see you all on the next one.